Let's first look at atomic bombs after reviewing how atomic and hydrogen bombs work. Those who've made atomic bombs know their principle isn't actually complex. Why can only a few countries make this junior high textbook concept? The main material for atomic bombs is uranium, with atomic number 92. It exists naturally as U-235 and U-238. U-235 has 92 protons, 143 neutrons. U-238 has 92 protons, 146 neutrons. Elements with same protons, but different neutrons are called isotopes. U-235 is more suitable for nuclear bombs due to its higher reactivity. In nature, 99.2% of uranium is U-238, only 0.7% is U-235, 4% U-235 is low-enriched uranium, 90% is highly enriched uranium. Low-enriched is for nuclear plants, high-enriched for nuclear weapons. How can this ordinary-looking enriched uranium cause such destruction? This is where nuclear fission comes in. When a neutron hits a uranium atom, it splits into two smaller nuclei, releasing 3 neutrons. Scientists found that atoms lose mass during fission. Where does this lost mass go? Einstein's equation shows mass converts to energy and vice versa. New neutrons collide with other atoms, causing more fission, creating a chain reaction that continues indefinitely, eventually releasing enormous, devastating energy. There are two main types of atomic bomb designs: the gun-type design, like Little Boy, and the implosion design, like Fat Man. Let's examine the Little Boy gun-type design. If we disassemble it, we'd find several rings installed at both ends, made of highly enriched uranium. The warhead's uranium ring weighs about 25.4 kilograms, while the tail's ring is 38.5 kilograms. At the bomb's tail is an electronic detonator, which serves as the ignition device. The detonator connects to nearby smokeless explosives, followed by a steel casing that wraps the nuclear fuel and detonation mechanism. This hole is for the barometric pressure sensor, which connects to the pneumatic system. In the middle is a long barrel. The uranium rings mentioned earlier are installed inside this barrel. This is a sensor that triggers the ignition device upon receiving a signal. These are safety pins that prevent accidental detonation during transport. This carbon-lined cylinder helps control the nuclear reaction's critical state. The front piece is a carbon plug with neutron initiators installed. These ensure proper chain reaction initiation. This device is a radar altimeter. It precisely measures detonation height. Atomic bombs are typically dropped from aircraft. Before dropping, the safety pins are removed from the bomb. 15 seconds after release, the barometric sensor activates, estimating the bomb's altitude. When it reaches a preset height, the radar altimeter activates. When it detects the bomb is 580 meters above ground, the electronic detonator fires, igniting nearby smokeless explosives. The resulting thrust propels the tail's uranium ring forward at 300 meters per second, colliding with the warhead's ring. This impact also activates the neutron initiators, which release a large number of neutrons outward. These neutrons immediately bombard the uranium-235 atoms, as mentioned earlier. When a neutron hits a U-235 nucleus, it quickly splits into two smaller nuclei, releasing energy as heat and 3 neutrons. These neutrons then collide with other nuclei, causing more fission. This chain reaction continues until it reaches a critical point, producing enormous energy, ultimately creating a mushroom cloud. The Fat Man bomb differs from Little Boy in design, using an implosion method. Let's examine how it works. Fat Man primarily uses Pu-239 as its fissile material, like U-235. When Pu-239 is hit by neutrons, it also splits into two smaller atoms, releasing 3 neutrons and massive energy. These neutrons then react with other Pu-239 atoms, forming a fission chain reaction. The Pu-239 core is in a subcritical state. To initiate the chain reaction and release energy, the core must reach criticality. This is achieved by compressing the plutonium core.